Hi guys, welcome to our lesson for today. So today we're going to be talking about what about inductive reasoning, right? This is a way of trying to reason under Euclidean geometry based on certain aspects of the concept of geometry that we're going to try and look at. But before that, let's just look at exactly what geometry is all about, and then we'll get on exactly what this inductive reasoning is all about. So remember that Euclidean geometry involves things that have to do with theorems, and those theorems can be theorems of triangles and quadrilaterals, but in this lesson we're going to only focus on triangles. There's also what we call the axioms. These are just your statements without reasons, which is the same as what a conjuncture is. This is a statement after you try and make your reasoning. And then the conjunctures, we normally form them using inductive and deductive reasoning. So we've spoken about deductive reasoning. Now we're going to try and look at what inductive reasoning is. The terminology is this inductive reasoning. This is a system of reasoning based on observations of measuring numerous examples. So for example, I cannot say anything about this triangle unless I measure the same lengths and the same angles in another triangle and in another triangle and in another triangle, and then at the end I then give a reason to say, because I've been observing this in all my triangles, this is the claim that I can make. That's what inductive reasoning is about. So you don't reason just from one calculation. No, you observe and you measure number of times. And then also we have a conjuncture. Remember, a conjuncture, this is a statement based on observations and measurements, right? And this normally links condition to a conclusion. So for example, if I say, I want you to tell me that this side is equals to that side, and the question is about proving that, you're going to try and measure and do all these things, which is what we call the inductive reasoning. From there, after you find that yes, the conclusion can be drawn that this side is equal to that side, that will then be considered to be a conjuncture, because now you are trying to make a conclusion based on the measurements and all your observations. So one example I'm saying here is if A, then B, that's what we are trying to say. So meaning if this is the case, then this is the conclusion. Now, what is a triangle? A triangle will be a closed 2D shape, because remember I said we are mainly focusing on triangles here. It has what we call 3 vertices. Some people claim these are corners, right? So these are corners of your shape. Any shape for that matter that involves line segments has what we call a vertex if it's one, and then vertices if it's many. And then it also has 3 sides, a triangle that is, which are normally between those vertices that we are talking about. Now, properties of a triangle from theorems, we have 2 of them. One is that the sum of all the interior angles of a triangle is 180 degrees. Now, you just need to remember what sum means, right? It means that if I add all my angles in a triangle, they must give me 180 degrees. So normally, if this is A, B, and C in the triangle, then your statement will then be angle A plus angle B plus angle C must equal to 180 degrees. And then your reason for that will then be sum of angles in a triangle. Remember, you just shorten them most of the time. And then we have what we call the exterior angle of a triangle is equal to the sum of interior opposite angles. Now, before we can even talk about this, one thing that I need to make a disclaimer of is, for you to talk about an exterior angle of a triangle, the triangle must have one of its sides Produced means extended, right? So if maybe side AB is produced to maybe a point D there, then you can talk about an exterior. But if you just have a triangle and then they join maybe one line from one of the vertices of your triangle, that has nothing to do with an exterior angle. It must be one side of the very same shape extended or produced, if we use the more correct mathematical term. That's how you can think about an exterior angle of a triangle. Please make sure that you understand this, because a lot of people, they just see an angle outside the triangle but just next to the triangle and they claim it's an exterior. No, only when one side is extended. Now, the two scenarios that I'm saying, maybe diagrammatically, let me show you what I mean, right? So some of them, you can have a shape like this, where that is A, that is B, that is C, and then this is point D. There is no exterior angle of a triangle here, because if you look at the line BD, it's just a line that is floating in the air. That has nothing to do with the triangle. But if I take a triangle and then extend one of its sides, then I can talk about this angle here between the extended line and one of the sides as the exterior angle of a triangle, which will be equal to the sum of the interior opposite angles. So please just try and make sure you visualize this so that it can be more clearer to you. Now, when we apply inductive reasoning to the sum of interior angles being 180 degrees, what you would then do is you would draw lots and lots of triangles and measure the angles. Now, measuring those angles will be us trying to see whether this statement will always be true with any triangle that we have out there. Right? So as long as it's a triangle, will it give us 180 degrees if we add the angles? That's what we're trying to do with the inductive reasoning. So I have just an exercise that I want to show you here. If I try and move my point around, right? And I'm sure you guys have your calculators there. If you were to press maybe these numbers, these angles that I have here, angle A, which is 71.43, angle C, which is 67.88, and angle B, which is 40.69, and add all of them together, they will give you 180 degrees, right? I can also try and play around with it and put it like that. It will still give me the very same nature of me having all the angles that are inside the 180 degrees. So this will be me drawing the many triangles that I was talking about and measuring each time. And after measuring, I then add them to try and see that will this be true for all my shapes. So as I'm moving it like this, I'm just trying to show you an image of me drawing the many triangles just so that I can apply my inductive reasoning. Because you don't just then say, no, it's a theorem, it's like that, and we can take it moving forward. So that's what I want you guys to please understand about inductive reasoning. It's all about observing a repeated exercise that will yield a conjuncture, which will then be the conclusion that we're going to draw from that. I hope that is a bit clear as well as to how to investigate these Euclidean geometry theorems and try to talk about them. But for now, I want us to take a quick ad break. When we come back, we're going to investigate this concept further. Please stay tuned. I'll be back just now. Hi guys, welcome back to our lesson. So we are still looking at inductive reasoning. Specifically, we are trying to focus on some triangles right now, just to see exactly how can we apply the concept of inductive reasoning on a triangle. Let's just remind one another what this is about. Remember, I said inductive reasoning is a statement that you make after several observations and measurements, right? So you try draw and measure, draw and measure, draw and measure, and then check whether the statement that you want to make will be true throughout. And then from there, that leads to what we call a conjuncture, which will then be a statement based on repeated observations that we actually saw. And then it leads to a conclusion, which will be maybe every time I add all the angles, they must give me 180 degrees, like we've just spoken right now, and which will then be considered as a theorem, or rather a property of a triangle. So that's what inductive reasoning is about. But let's just see, how do we now apply this inductive reasoning? So when you apply the inductive reasoning to find out more about triangles, we try to observe and measure, as I showed you. We develop a conjuncture. Developing a conjuncture will be, after I see that this is what has happened, I can then make a statement, and that statement will be considered as a conjunct. Then I will need to test my conjunct. The testing will be, is this true for all of the shapes, right, that are triangles at that particular time? What must be the condition for the triangle to adhere to the conjuncture that I said? Then this is where we talk about your variables that you control, or your independent and dependent. And then you disprove by a counterexample. And now here you will see that we only just need one thing to disprove what we have been trying to talk about. So you can make a conjunct and just find one flaw, that maybe if I have three lines like this, right, you'll find that if this one is longer than the sum of these two lines that I have here, then this will not form a triangle. That's one of the statements that we can make to try and disprove that a triangle is formed by any three lines. Because some people, that's what they say. So that's what you need, just one thing to disprove it. From there, because now you've disproved it, you then try to refine it by then saying, if we control the length of the longer side of our shape, so that maybe it is equals to the sum of these ones or less than the sum of that, because I'm trying to use this example as we are going to investigate it, then it will always give me a triangle. That's what I would then do as a refining of my conjunct. Then lastly, I will then prove by deductive reasoning. Remember, deductive reasoning will be where I then throw in the properties of these particular shapes based on geometry of 2D shapes. Now, remember, what is a triangle? We said this is a closed 2D shape. It has three vertices. It also has three sides. And then one conjuncture we can make is, a triangle can be formed by joining any three vertices with three line segments that are each joined to two vertices. What does this mean? It means that I'm saying I have one point there which I will call A, I have another point there which I will call B, I have another point there which I will call C, right? And then I have a line there, I have a line there, and I have a line there. If I join all these three lines, right, each line will need to be between two vertices. That's what the statement say. So my A will be maybe the top, and my B will be somewhere there. And then the other line will be between B and C, and then the other line will be between A and C. And then if I join them at the end, then they lead to me having a triangle like that. That's what this conjuncture says, right? But do you think we can disprove this conjuncture? We are yet to see it just now. Now, also, the converse of this, remember, converse will be just when you start with the conclusion, right? If A is true, then B is true. Now, This is a statement that starts with a conclusion of a theorem or conjecture and then try to end with the conditions that made that conclusion to be true. If these two triangles are similar, if they are congruent, then these are the conditions I can take from that. If this line is equal to that line, these are the conditions that would have led to me saying that. That's what we are saying when we say this is a converse. And then a statement will be if A, then B is true. The converse of the statement will then be if B is true, then definitely we know that A will be true because B was a result of A. You see. So that's what we are talking about in terms of a converse and a conjunction. Now, what do we need to look at here? We said a triangle can be formed by joining any three vertices with three line segments that are each joined to two vertices. The converse of this will be a triangle now can be formed by joining any three line segments to three vertices. Let's look at this. We said our conjecture was we must have three vertices. And if we have three vertices and we join them with three line segments, I will just say lines in this instance, and then this will give me a triangle. The converse now says, if I have three lines that I joined between three vertices, it will give me a triangle. So you can see, if I say this is A and that is B, if A is true, then B will be true, right? And then if B is then the case, it means A is true because B was a result of A. You see, I really, really hope I am narrating this clearly so that you can see what this is. Now, one more conjecture that we can talk about is a triangle can be formed by joining any three line segments to three vertices. Now, what I want us to do with this one will be to investigate this one now. So if we look at this, I have three line segments here. I can play around with the lengths of my line segments to suit what I want to try and do. Now let's try see if I want to join them and make them a triangle, will it give me a triangle or not? Right? Look at this. This does not give me a triangle. There's an opening up there. So as a result, what will I need to do? Maybe extend this length to be there, right? But what would that be doing? That would be disproving the conjecture that we just made. Because remember, we said we need just one thing to disprove a conjunction. But if I play around with this again and say, maybe let me make my angles to be a bit bigger than what they are right now, and then I join that there. Do you see? Still, it will not give me the triangle that I want. Because if you look at this, you'll find that the orange line is bigger than the sum of the yellow line and the purple line. And I know that we've spoken about the theorem of Pythagoras earlier on in our lives when we were starting to do maths. And they always told us that a triangle must always have the longer side equal to the sum of the other two sides at all times, you see. So that's what we are talking about. And then if I extend it, then it can give me a triangle. So you can play around with this until it makes sense to you by just trying to then make it a point that it still upholds to what we're trying to talk about. But this simply tells us that we cannot just join any three line segments to any three vertices, right? That's not the case. But if I do, and I have observed certain things, it will give me a triangle. But we saw that with others, there was an opening at the top there, or an opening at the bottom where it was not a closed 2D shape, which we've been trying to emphasize. So what does that tell us? We go back. We tested the conjunction, right? by saying if I join 3 line segments with 3 vertices, I get a triangle. That was my conjecture. We tested it and we saw that there's certain conditions that disprove this conjecture of ours, right? Where maybe one length is longer than the sum of the 2 lengths that we have. Now, to refine it will then be to say, what can we now say that will make our conjecture to be true without any faults or any conditions where it will not become true? And then we will prove it by deductive reasoning. In this instance, remember in terms of conjecture 2, this will be a triangle can be formed by any 3 line segments to 3 vertices. But a triangle can be formed by joining 3 line segments so long as the longest side is always less than the sum of the other 2 sides or equal to the sum of the other 2 sides. That's the revised conjecture based on us going back and saying, but this has been disproved because we saw that not all the line segments that we can claim we want to join, they give us a triangle. This one did not, but this one did. And with this one, what we found is the longer side must be equal to the sum of the other 2 sides or less than the sum of the other 2 sides. And then that's what will then be our revised conjecture based on what we are trying to talk about in terms of inductive reasoning. Then you can try and use deductive reasoning to prove this, which is the theorem of Pythagoras that we will try and use, and I promise you it will forever work with any triangle that you have for that matter, as long as that theorem holds in that triangle. All right, guys, we just need to go quickly to an ad break just to freshen up a bit. We are still looking at inductive reasoning. Please be back after the ad break so that we can investigate more about these triangles that we're trying to look at. Stay tuned. I'll be back just now. Hi guys, welcome back to our lesson. So we are still looking at the inductive reasoning approach, right, to geometry. And this has been mainly focusing on triangles because there are some theorems that we can try and disprove based on just one point that will disprove not really a theorem but a conjecture that we make based on observations, because that's what inductive reasoning is all about. So let's look at some more examples. But before that, we need to just go back and look at how did we say we apply this inductive reasoning and then reapply it to one more or two rather examples that we're going to try and look at just to see exactly how does this process work. So remember we said when you're applying inductive reasoning, you observe and you measure, and then you develop a certain conjecture, but that conjecture can be tested on different occasions where you draw, measure each time, and then you find that there is one discrepancy that disproves that particular conjecture that you made. Then you would need to go back and refine it, meaning refining would simply just be a process where you say, okay, if we can fix this concept, right, this line must always be in this nature, this angle must always be in this nature, then we use the deductive reasoning to prove what we've just tried to then put as a conjecture. Now, a third conjecture now in our lesson is, in a right-angled triangle, each of the other 2 angles measures 45 degrees. Now, I know for a fact that as you are sitting there, you already know that this is really not always the case, right? There must be a certain special condition of that right angle triangle that will make this to be true at all times. I know you know it, so yes, exactly what you are thinking now, that's the correct one. But let's just try and see the examples of what we are trying to look at, right? So you can see if this is 45 degrees, that is 45, I'm gonna add them, they give me 90, plus my square there, which normally means 90, it's 180 degrees. We just said one of the properties is sum of angles add to 180 degrees. Again, even if it's facing down, there's 45 there, 45, add them, that's 90, plus my other 90, again, 180 degrees. So you see, these are conditions where it's quite very nice, and I am able to prove that this is true, right? But one of the things that we need to look at here that I'm going to try and show you as well is this is not always true with the triangles, right? So if maybe this is 90 degrees, it's just that it does not go exactly to 90, but I will just try and make it 90 just a bit. So you see 90.19. And then I have my other angles the way they are. Maybe let's try and make this 45 if it's possible to do that. It goes, yes, there, but it just moves my, yes, let's see. All right, so if I have something like this and I want to try and talk about this theorem where I say in a right-angled triangle, I must always have the angles giving me 45, 45. At times, do you see? Yes, that is 90, that's true. But the other angle is 45.1, so it's 0.1 more. That one is 0.1 less. And this will still give me 180 degrees. So exactly what does this mean? Is it always true that in every triangle, that is a right-angled triangle, my two angles that are not the 90 degrees must always be 45 degrees? Not really, because we are seeing that even if you move it and you still have those three angles the way they are placed, but one of them is 90 degrees, if you add them, they will forever give you 90 degrees, 180 degrees, right? So that's what we are trying to say here with this particular thing. But now, we can give an infinite number of examples to try and prove this conjecture. But is it always true? That's what I want you to think about. And I just showed you now that even if we adjust 0.1 less and 0.1 more with the two angles, they will still give us 180 degrees. And then one of the special cases that I can give you is this one here, right? Where this is an acute angle, which is 31. That is an acute, which is 59. And if you add 31 plus 59 degrees plus 90 degrees, all of this is going to give me exactly 180 degrees, right? But my conjecture was claiming that J and L must always be 45 degrees if this is a right-angled triangle. Now, what can we do to try and refine this? We'll then say, let's add one more interesting fact in this, to say not just in any right-angled triangle, but it must be right-angled and isosceles. Then each of the other two angles will definitely measure 45 degrees. And that's what we then mean about this inductive reasoning. Guys, I promise you, if you want to really understand your geometry, you need to try and talk to the diagrams, talk to the conjunctures, talk to the theorems, and try to see what are the things that, should they ask me in a different way, will then make me not see what they want me to see, right? So even in this one, you can really see that if I tell you that the angles must add up to 180 degrees, it means it doesn't really matter what the angles are inside the triangle. As long as all three add up to 180 degrees, then that shape is a triangle. it's a 2D shape triangle that has 3 lines and 3 vertices. So that's what you try and do with this concept of inductive reasoning. Let's just quickly remember. You make a conjuncture, right? After observing and measuring, you refine it, not really refine it, you test it, right? By checking different conditions of the very same conjuncture that you made. Based on those, you try and refine it and see whether I can make a provision where it will make my conjuncture to always be true. And then you try and give a refined conjuncture by proving it using the deductive reasoning, right? So at all times, you really, really need to make sure you understand this. So let's try use deductive reasoning to prove this particular conjuncture here after adding this one more point. Now, what point is this that we said? We said the point is it must be an isosceles triangle. So you can see this is AB is equals to BC. I know that, right? So I'm going to draw my table then to prove it using deductive reasoning. And then I will then say this is a statement and that is a reason. So my very first statement will then be AB is equals to BC. And this is because we can see it on the diagram, so this is a given. Therefore, it means that angle A will be equals to angle C, and the reason for this will be angles opposite equal sides. Some people claim it's isosceles nature of a triangle, right? But please don't use that particular reason as a reason for a statement. But now, what do I know based on this? I know that angle A plus angle B plus angle C must amount to 180 degrees. And my reason for this is sum of angles in a triangle. And then from there, based on this, I will just say I have 2A plus 90 degrees is equals to 180 degrees. Now, where does 2A come from? You can say 2A or 2C. It's really up to you. Remember, A and C are equal, right? So when you add 2 equal angles, they give me twice that angle. And then from here, this will be 2A is equals to 90 degrees. If I subtract both sides by 90, then my A will be equals to 45 degrees. But remember, what did we say? A was equals to C. So it means both A and C are 45 degrees. And that's what we mean when we say prove this using the deductive reasoning. Because all of this is me applying the properties. I know this is given. This is a property of an isosceles triangle. It doesn't matter whether it's right angled or not, as long as it's isosceles. Then the angles opposite those equal sides will definitely be equal. This is a property that we've spoken about in this lesson where we say sum of angles in a triangle must be equal to 180 degrees. And then going down is just my basic algebra of trying to find what the value of A is, which will then eventually give me the value of C as well. So that's what we mean when we say apply the deductive reasoning to try and prove your conjunction. So what is our conjunction? Conjunction is in a right-angled triangle. Given that it is an isosceles triangle, then the two angles will always measure 45 degrees. And then we saw that we can prove that using the properties of an isosceles triangle and the properties of any triangle that the angles add up to 180 degrees. I really, really hope this is kind of giving you some goosebumps, because trust me, it is giving me goosebumps thinking about it, just how beautiful a thinking process can be. From just saying we don't know anything, I drew a diagram, I measured using protractor, ruler, And based on this, I try to make a conjuncture, which is a statement that can be disproved. I try to find a flaw, and then I try to refine it, and then later I prove it using the actual theorems that they've been revised a long time ago. And that's how we try to do geometry. Guys, please stay tuned. I want us to take a quick ad break so that when we come back, we can then apply this to the concept of parallel lines and see exactly how can we talk about this concept, because there's these misconceptions that people throw out there with triangles and a parallel line in between the triangles. But stay tuned so that when you come back, you can then learn more about what I've just said. Now, I'll be back just now. Hi guys, welcome back to our lesson. So we are still looking at the concept of inductive reasoning, right? This is all about trying to measure, and observe, and then make a conjuncture, refine it after we disprove it, and then prove it with deductive reasoning. Now we're going to look at the concept of when we have some midpoints of the triangles and drawing a line through those midpoints, and what does that do to our triangle. But let's just look at it so that I don't then make you not know exactly what we're talking about. So just remember, we're always going to look at you remembering what this inductive reasoning is about. I said observe and measure, develop, test, disprove, refine, and then prove again. Now, here, one of the conjunctures that we can try and make here is, in a triangle ABC, a line drawn parallel to the third side of the triangle, right, which is AB. What is it that can we say about this, right? And at a later stage, you will see that it's one of the theorems that you actually have in Euclidean geometry, right? That it actually passes through the midpoint. But I want you to think about that, and we're going to investigate it to say, really, is that the case at all times? Or is it just a special condition when it is passing through midpoints, and then there's something else that we can know based on that, right? So if we look at this, we're saying the line drawn parallel to AB joins the midpoints of AC and BC, which is just what I said to you, right? So in simple terms, it tells us if I make this to be D and that E, AE will be equals to EC, BD will be equals to DC. That's what it simply means, right? That's what this conjuncture is saying. But is this true for all of the conjunctures or not, right? All of the triangles, I mean. We really don't know. So let's try and see whether this is actually true. Now, if we look at this diagram that I have here, right, you can see that if I have DE being the line parallel to AB, I just really can't show the parallelness here with my arrows, but I try to show it with the angles. You can see that 120 plus 60 will be equal to 180 degrees, which will make it co-interior angles, right? It doesn't really matter how you move this particular shape. At all times, it will always be the very same thing that we are trying to say here in this triangle, right? Where if I move it like that, it will forever be when it is passing through the midpoint. That white line, don't worry much about it. I'm gonna really address it just now to show you exactly what that one is about. So you can see that with this particular theorem or this conjuncture that we have here, it's not always the case that any line drawn parallel to AB joins the midpoint of AC and BC, right? But now, if we try to disprove this particular thing by using what we call the the deductive reasoning, you will see that if I claim, right, that this is a triangle, and then I draw a line that is parallel to that line, there is really no way of me proving that this line is equal to that line, or this line here is equal to that line using the deductive reasoning, because there is no theory behind us talking about that, right? So when we're trying to now refine this, we will then say, firstly, how can this be looked at if it's the inverse of it, right, or the converse of it? It means that if I say I have a triangle ABC, the line that joins the midpoints will forever be parallel to the third side. This becomes true because, yes, the condition is that it must be passing through the midpoint of the two line segments, right? But can it be true if it's not passing through the midpoints of the line segments? That's what we are really battling to try and understand here is it really true that even if it's not passing through the midpoints, for any triangle that we have, will it still be parallel to the third side or not? And that's what we need to look at, right? Because this will then say, if any line is drawn parallel to the third side, it is passing through the midpoints. But that is really not a true statement at all times. But let's look at this. So we're saying the line that joins the midpoint is parallel to AB that we've just spoken about. Now that it is actually going to be the case, right? This will be midpoint of that. So this is A, D there, and then B here. This is equals to that, and this is A, E, C, and this is also equals to that. There's many ways we can try and prove this, right? Because you will see that this angle will be equal to that angle there because of corresponding angles, and then this angle here will be equal to that angle there. And then you can try and talk about having an isosceles triangle where you will then make a claim that this side is equal to that side, right? That's what you can try and do. And then one thing also that we are saying is, if you're trying to prove the converse of this conjuncture, we will also be using the very same thing where we consider the concept of similarity or congruency that we're going to look at. However, that's not really what we want to focus on more here. The concept is just to try and investigate what this concept of drawing a line parallel to the other two lines, what does it really do for us? Now, I want to show you something as well with this line of mine that I said I was going to show you, right? Because remember what I said. They said if we draw any line parallel to AB, this line will be passing through the midpoints of the two line segments. Now, if you look at this, right, if I put it on the line like this, it simply tells me that this line is parallel to this line, right? But do you see, I can put it here. It is still parallel to it. It does not mean that it is passing through the midpoint because the midpoint is E and D. I can also move it up there. It is still parallel. It does not pass through the midpoint of BC and the midpoint of AC, but it is still parallel. Even if it does pass through it, it will definitely be parallel to it. So do you see, it's not just about it passing through the midpoint only. And that's what I wanted you guys to see in terms of the flaw that we can find to try and disprove this particular theorem that we are talking about here, or rather this conjuncture, that it must only be passing through the midpoints. That's not the case, guys. Guys, I really, really hope all of this is a bit clear on how to try and investigate Euclidean geometry, right? Just to summarize everything we've looked at, we said inductive reasoning is a statement we make based on observations and measurements. It has nothing to do with theorems. No, you draw, you measure, you draw, you measure, you draw, you measure, and then you make a conjuncture. This conjuncture will be what leads to a conclusion that if A is true, then B will definitely be true. and then we looked at the converse of this, right? But the process of this inductive reasoning, we said, is all about observing and measuring, and then trying to provide or form a conjuncture to say, I know that if it passes here, this is what will happen. If it goes through that point, this is what will happen. So it's all about what did you see with your eye. That's why I'm keep on using my hands, just to show you. If you see this, it simply tells you this, right? Same as if you see that, it tells you this. So that's what we are trying to say. That's what a conjuncture is. You test it by performing several measurements and observations, and then you refine it. If there's changes that need to be made, you prove it using the deductive reasoning, and then from there you can then try and link it to a certain theorem that we're talking about, guys. But right now we actually have come to the end of our lesson. I really hope you are clear now on the difference between deductive reasoning, which is using the properties that are already set, and inductive reasoning, which uses what we see after we try and measure and draw. But from me to you, I hope everything is clear, and you can always go back and do your own research, please. Because remember, I always say, don't take everything I say as is, right? If you don't understand something, don't just say because he said that, then it's correct. Go investigate so that it can make more sense. Mathematics is food for the soul. Until next time.